Hello, everyone. My name is Anu, back again, and today we're talking about Buckingham PI, which is actually one of the most useful concepts in chemical engineering, in my opinion, because it directly applies to everything we do with scale up. What I mean by that. Suppose you have a system that you've been running in the lab. It's small pipe, small pump, small everything, and it's working pretty good. And you're ready to take the data that you've learned and you've picked up and transfer it to a larger system. So the question becomes, how do you do that? And Buckingham Pi is actually one of the useful things that actually allows us to scale up things in a way that we keep the same physical phenomenon from happening, right? So let's actually get into it. So I'm just going to write out Buckingham Pi first of all, and I'll tell you what it is. And then afterwards, we'll actually go through an example and actually derive some of these values for you, right? So what Buckingham's pi states is that if a physical phenomenon can be described as a function of n variables, so a physical phenomenon is equal to a function of n variables, right? So we have x1, x2, x3, dot, 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 all the way to xn. So n different variables. And we have k fundamental dimensions, which I'll tell you what those are in a second. So k fundamental dimensions. Then we can actually describe the physical phenomenon as a function of n minus k dimensionless numbers, which we actually call pi groups. So pi 1, pi 2, all the way to pi n minus k. So now that I told you what all this is, let's actually talk about what a fundamental dimension is, because that's actually the crux of this, right? The most important thing. Right? Now suppose you're probably familiar with units and unit conversions. Suppose I give you a velocity equal to 2 meters per second, and then I ask you, okay, what is that in centimeters per minute or something like that? Well, you would say, okay, I can convert that. I know that there are 100 centimeters in 1 meter, and there are 60 seconds in 1 minute. And so then you can do the math, and you get 12 from 20, 12,000. If I did my math right, 12,000 centimeters per minute, right? Very easy. We can do these unit conversions. Now, of course, it's not about unit conversions, but the point is there are different ways to describe velocity. But in general, velocity is some length per some time. So this is what we call fundamental dimensions. So stuff like meters, centimeters, inches, these are units of length. Things like seconds, minutes, hours, these are units of time. Things like kilograms or pound mass or slugs, which is a crazy name, by the way. This is mass. Once we get into thermodynamics, we have stuff like temperature. So Fahrenheit, Celsius, Kelvin, these are all temperature. And so we can describe almost anything in terms of well, not almost everything. Every physical phenomenon we can describe in terms of fundamental dimensions. So for example, force is equal to mass times length over time squared, right? In other words, mass times acceleration, right? It doesn't really matter what we choose for the mass or for the length or for the time squared, as long as we've put in the format ml over t squared, then it's a unit of force. So stuff like kilograms, meters per second squared is just as valid as pound mass times feet per second squared. Both are equally valid units, right? And the most important constraint, of course, is that you have to have the units matching, right? I can't just add a velocity and a force. Like that doesn't work. And the reason this doesn't work is because they have different units. They have different fundamental dimensions, so they can't really interact with each other. Now, what does it mean for something to be dimensionless? Something like a pi group. It means it does not matter what the fundamental dimensions are. It has no dimensions, or it has no units. It's a number that has no units, essentially. And so you can imagine if I have let's say I have a lab scale pipe, small, maybe it has a one inch diameter. And now I'm going to a production unit. It's not realistic to say that they're going to have the same inner diameter. That's just not realistic. This might be something closer to 10 feet. So we went from 1 inch to 10 feet. It's not fair to say that they have the same because we are changing our length. We're going to a different scale. However, suppose I told you that there was a dimensionless number associated with this pipe, and that was equal to, I don't know, 30,000. That's just a number I make up. I like that number. Since it has no dimensions, it shouldn't matter how big or small the system is, which means that our larger system should also have that dimensionless number also be 30,000. And this is what allows us to scale things from small to large. There are a lot of dimensionless numbers or dimensionless groups that we can derive with Buckingham pi. And we need to make sure that when we scale up from a small to a large system, that the dimensionless numbers are matching. So just for fun, let's actually derive one of the most famous and commonly used dimensionless groups that we use in chemical engineering. So suppose we have a pipe and we have a fluid flowing through. And the question we want to ask here is, what is the dimensionless number that actually describes this flow? So the physical phenomenon we are talking about today is flow. So what are the variables that flow is a function of? Well, so it could be a function of the density, right? Water is going to flow very differently than air because water is more dense. Obviously, the pipe diameter is going to be a big deal, like how big the pipe is. Things like the velocity of the fluid. A faster fluid is going to flow differently than a slower fluid. And then the viscosity. This is essentially how fast or how viscous is the fluid. Molasses is going to flow a lot differently than, say, water or oil. So this gives us 4 variables, right? N equals 4. Okay, and we care about mass, length, and time. Those are our 3 fundamental dimensions. So K equals 3. Therefore, we should have N minus K, 4 minus 3, equal to 1-dimensional group. So we can actually say that the flow is a function of 1 dimensionless group. And a goal now is to figure out what that dimensionless group is. So first, let's take each one of these units and actually put them in terms of their fundamental dimensions. So for example, the density is mass per volume. which is length cubed. I like to put everything in one line, so I'll use the negative exponent here. Diameter is pretty simple. This one's just a length. The velocity is length per time, or LT minus 1. And the viscosity, which if you're pretty new to chemical engineering, you might be new to, but this is mass over length times time, or m L minus 1, T minus 1. And so we know that our pi group pi is equal to rho to some coefficient, d to some coefficient, times velocity to some coefficient, times the viscosity to some coefficient. We can actually put these in terms of our fundamental dimensions here. And we know because pi is dimensionless, it has no units, the exponent should equal 0. So now we have a system of equations that will allow us to actually solve for A, B, C, and D. So, for example, if we look at the mass, we get 0 is equal to A plus D. If I look at the length, I have 0 equals negative 3A plus B plus C minus D. And then lastly, time, you have minus C minus D. Okay, so now if you actually solve for each of these values, you'll see that A equals 1, B equals 1, C equals 1, and D equals negative 1. Which means that our pi group is equal to rho times velocity times D over mu, the viscosity. And this is our dimensionless group. This actually has a famous name in chemical engineering, which is the Reynolds number, which describes fluid flow in a pipe. If we have a pipe in the lab that's running at 30,000 Reynolds number, when we scale it up to a larger unit, say a production unit, in order for the flow properties to be the exact same, we have to have a Reynolds number of 30,000. Again, we have to have them equal at both scales. Now, I'd like to end this by showing you some common other dimensionless numbers that you might see out in the wild as a chemical engineer, right? So obviously the Reynolds number we just talked about. This is rho VD over mu, which is essentially the inertial fluid forces over the viscous fluid forces. Forces caused by the inertia of the fluid versus forces caused by the viscosity of the fluid. And depending on what the Reynolds number is, you'll typically have different fluid properties. You'll learn about laminar and turbulent flow. When you have viscous forces dominating, things tend to be very smooth and what we call laminar flow, versus if you have inertial forces dominating, things tend to be more chaotic and we call that turbulent flow. Another one, I'll go into heat transfer here, is called the Biot number. And the Biot number, which is HL over K, this is the ratio of external convection over internal conduction. So if you remember, there's different types of heat transfer: convection, conduction, radiation. And essentially, a great example of this one is, let's say you have a ball of some material and you put it inside an oven, a really hot oven. So you have heat transfer from the surrounding air via convection, and then you have heat transfer inside the actual material itself, and that's conduction. And the question is, which one of these is faster, right? So for example, if you have a low BO number, internal conduction is very high. So suppose you took a metal ball, like a solid metal ball, and you put it inside the oven. Well, in this case, conduction is pretty fast for metals compared to other materials. So what happens is you get a pretty low BO number. And one of the great assumptions you can make with a low BO number is that the temperature profile throughout the solid is uniform. Basically, there's no temperature profile. Whatever the temperature of the surface is, that is what the temperature you can assume roughly to be the same in the center. Because the rate step, the heat transfer limiting step is the convection. Now, the opposite is true if you have a very high BO number. In other words, conduction is really slow. Let's say you have a plastic ball or like a really good insulator. Then convection is going to be much, much faster than conduction, in which case you have a temperature gradient across the ball, and then your heat transfer problem becomes a little bit more complicated and involved. So then the last one that I'll teach you is the Domkohler number. And the Domkohler number, there's actually two of them. So I won't go into what each one of them are, but let's say I'll give you one of them, for example. And this is K, this is the second one. K times C to the n minus 1 L squared over the diffusivity between A and B. This is molecular diffusivity. You don't need to worry about what these are. Just know that this is a dimensionless number. And this essentially tells you the rate of reaction compared to the diffusion rate. Both Domkohler numbers do this, Domkohler 1 and Domkohler 2. And essentially, this is very important in reactor design, because the question becomes, am I reaction limited or am I diffusion limited? Right? And that's going to change how you design your reactor. Suppose you have a catalyzed reactor. So you have a catalyst. And then the question is, okay, I'm increasing catalyst or I'm changing some part of my property. Do I need to, what's the biggest lever that I can change? Do I need to do things that will increase my reaction rate? Or do I need to do things that will increase my diffusion rate? Because those are two different things, right? And so hopefully now that we've gone to the end of this, you can see the value of having dimensionless numbers and actually going through the practice of deriving these through the Buckingham PI, and how we can use these to scale from a smaller system to a larger system using just very simple values that we know. All right, so that's it for this video, and I'll see you tomorrow in the next one.